Hi, my name is Stacey, and I am a postdoctoral research associate in the Center for Sustaining Agriculture and Natural Resources at Washington State University, located at Puyallup Research and Extension Center. And I'm going to talk to you today about biochar and co-composite biochar in strawberries and potatoes. My one-sentence line there on the first slide: in the short term, one growing season, and when used as a soil amendment, composted biochar is more beneficial than biochar alone. So, as a reminder, what is biochar? It's a solid, porous, carbon-rich product made from biomass such as wood, manure, and crop residues, though not limited to those feedstocks. It's heated in a closed container with little or no air, generally called pyrolysis. And biochar is distinguished from charcoal by the end-use application: charcoal for fuel or energy, biochar for carbon sequestration and environmental management, or as a soil amendment. Why would we be interested in biochar? There's really two sets of reasons. One has to do with waste, and the other has to do with soil. 28.5% of Washington state waste streams are organically derived. That includes animal manures and yard waste. An additional 12.3% of that are characterized as wood waste, and 1.7 million megagrams of material are available for established programs like compost production or emerging industries like biochar. In addition to that, there are potential benefits of biochar when it's used as a soil amendment. Those include improving porosity, water holding capacity, cation exchange capacity, carbon sequestration, and nutrient cycling. In addition to that, it can be used in the treatment of organic and inorganic contaminants in soils and water, and it may have an effect on soil microorganisms. The majority of biochar interest, though, stems from its use in soil and soil-like media, though. It's important to remember that the effects of biochar on soil are heavily influenced by soil texture, the particle size of the char, and how it was produced, and the rate at which it was applied. In that same vein, you can see that biochar feedstock temperature and age affect the properties. In the middle column, you see low temperature effect on the biochar properties in the left, and in the right-hand column, you see those effects in the high temperature. There's really a reversal of some of those properties when that temperature goes from low to high, and of course these are just generalized, roughly 300 to 350 C for the low temperature, and the high temperature ranging somewhere between 600 and 900 C. That can vary, of course, due to the feedstock. But the important thing to remember is char is not uniform. Temperature has a big influence on its properties. Feedstock has a big impact on its properties, as well as its age. If you look down at the bottom section of that table, you'll see negative functional groups. The charge is fewer in younger chars and more in age char. So age has to do impacts the physical chemical properties of the biochar itself. Why would we be interested in composting biochar? There are some benefits that have been suggested after much research. The higher compost peak temperature, higher CO2 emissions, which is not necessarily great. You have enhanced compost pile structure and aeration, decreased N loss in that end composting product, reduced ammonium and other greenhouse gas emissions, which contradicts that CO2 emissions there, so likely the methane and nitrous oxide. And it may alleviate phytotoxicity by stabilizing heavy metals. For this project, we mixed the biochar, which I'll discuss later, at a municipal facility listed up there at the top of the slide, Lens Enterprises, at 5% volume by volume, which was used thereafter in the field trials. Those field trials went into two locations, one in Mount Vernon in potatoes, one in Puyallup in strawberry. You can see the similar soils, but unique in their own properties. At each one of those, we applied 5 different amendments, including a control. We applied the biochar alone on its own. We had a control plot that was completely unamended. We applied a compost that had no biochar in it. We applied a co-composted product, which was composted at that 5% volume by volume. And we mixed the compost, so the middle there, with the biochar in the field at the time of application as our 5th and final treatment. This was replicated 4 times at each site in a split plot. You'll see the main plots there are fertilized and unfertilized, and the subplots were the amendments themselves, again replicated 4 times. As I said, it's important to understand the properties of the biochar. So let's take a look at that very quickly. Our biochar was a high temperature biochar at about 1600 F or 870 C. And you can see the distribution of the particle sizes. A majority of those particles were in that 1.6 to 3.3 millimeter size. The percent carbon was 88.3 with a surface area of 533 meters squared per gram. Here are some properties listed for the amendments themselves in 2018 and 2019. That product sat between those 2 years and then was used in the 2019 application. So same product, 2018, 2019. A couple of things to note. You don't see a lot of difference in the percent carbon between the compost and the co-compost at 32%, but you see pretty good differences in between the nitrate and ammonium between those 2 products. Again, apparently my wireless is kicking on. In 2019, you see high levels of nitrate and ammonium because that sat and was allowed to evolve there. These are the treatment rates for those amendments. If you look at the treatment on the left-hand side, and let's just take yards per acre, so the middle rate column there, you can see how much material was applied to each one of, I think that was total plots actually, to all the plots. So we have a different application rate for all of these because we were trying to equalize the amount of C. The bottom note there on the slide, the amendments were applied at 3.9 tons of organic C per acre or 8.75 megagrams of organic C per hectare. So same rate of C, different rates of material. We had an issue, however, with the biochar in that when we calculated the bulk density of the material, it was at about 5% moisture, and over time, as it sat outside, it gained moisture, probably near 25 to 30%. So we actually applied this at a much less amount than we intended. That was corrected in the 2019 season, but you might see that in the data, and I will bring that out when we get to it. We collected crop yield, bulk density, nutrient availability, and total and particulate C. In 2018, we see yield production in potato here in Mount Vernon. Moving left to right, biochar in the yellow, compost and the co-compost in brown, the compost plus the biochar in the field in orange, and the gray is the control. No statistical differences in the unfertilized in 2018 and 2019 and the fertilized in 2019, but we see statistical differences in the tuber yield owing to partially the amendment itself. Not unexpected. We see the control and the differences between the control and the co-composted products. If we look at strawberry in year 1, same color scheme to the amendments, we see no statistical differences in the fertilized and unfertilized. That's fertilized on the left and unfertilized on the right. We learned that it takes a while for strawberries to mature, so we went back in the second year and collected the fruit, and we see statistical differences largely between the amendments themselves and the biochar only. No statistical differences in the unfertilized portions in any of the amendments or the unamended control. As far as physical measurements, we analyzed bulk density in 2018, so this is 2018. In Puyallup and Mount Vernon, you see similar trends with the amount of material that is applied listed there on the bottom in the bar columns, 21, 29, 29, 24, and 0 yards per acre. Only in Mount Vernon do we see statistical differences, and the largest ones there between the compost and the unamended plots. In potatoes, mid-season nitrate end results varied somewhat by year. The co-compost and the compost tended to be greater, especially in 2019. I'm going to draw your attention to 2019 here. These are two, again, one-year experiments. Amendment is applied, data is collected, location is moved, amendment is applied, data is collected. This is what you would expect to see, these trends here, the unamended and the biochar plots at the lowest nitrate levels and increasing with compost and biochar, compost and co-compost. In 2018, it's unexplainable to me why we saw the trends we did there. It's possible there's some artifacts of previous research that may have had an effect on what we saw in the soil. If we continue, here's a little bit more in-depth look at the inorganic N, and these are in the unfertilized strips in the mid-season soil nitrate and ammonium in Mount Vernon. That mid-season was collected at 44 days. Here is the total N's applied pounds per acre. You can see the co-compost with the amount, the highest amount of nitrogen. We then calculated the available N per acre, and again, co-compost with the highest amount. The N that is available in the biochar, though a lot lower, a much lower number, is nearly all organic with small, very small, 0.52 ppm of inorganic N, and I think that's mostly nitrate. If we look at the differences in mid-season nitrate and strawberry, kind of a similar thing. Right-hand side, 2019, so a different location. We see a similar trend to the potatoes. No amendment in biochar and compost and biochar at the lower end of the nitrate levels. Co-compost and compost at the higher ends. No real differences in that 2018 year. Somewhat unexplainable to me. We take a look at total and particulate C relative to the amounts of amendment applied at Mount Vernon. These were collected at 14 days post-amendment in the 0 to 6 inch depth. And what's interesting here is that we can look at the tons of amendment there across the bar columns, 12.2, 12.2, 7.4, 4.5 in each one of those research plots, and calculate the tons of organic C. And I said we tried to equalize the amount of organic C going out into the plots minus that bulk density air where the moisture was higher than we calculated, so we have a little bit less of organic C going into those plot, and that kind of mimics what you see here. I think maybe the biochar is only because of that lower portion of C. You'd expect these all to be about even in comparisons with the unamended control. It also may be an artifact of the sampling procedure, as the total volume of biochar is much less than what you see in the actual volume of the amendment to the plots themselves. There's a possibility that there could be some influence on the native C cycling, but I'm not sure that that's correct. If we look at the C to N ratios in the particulate and total matter, again, 0 to 6 inches in Mount Vernon, we see what we'd expect in the trends. The C to N applied in each one of these plots reflects what the C to N ratio is on the data we collected. We look at CEC quickly, and we see a similar trend between the two sites, where there's no statistical differences in Mount Vernon plots, but in Puyallup, biochar, compost, and co-compost increase the CEC compared to the compost, biochar, and unamended controls. And finally, we look at some nutrients in the soil, alternate nutrients, potassium, magnesium, sulfur, and zinc. And in each one of these, co-compost and co-compost, compost and co-compost amended plots see significant increases in some cases with the biochar, in other cases with the unamended controls, not unexpectedly, as those nutrients are in the compost and co-composts themselves. So clear as mud, right? Conclusions quickly: compost and co-composted materials are greater than biochar alone. Yield, soil bulk density is affected by the quantity of the material added. The biochar rate dependent and compost increase soil CEC. Biochar may have an effect on native seed cycling. And off of this project, we initiated two additional projects, a replicated composting experiment utilizing biochar as a feedstock, and we're currently partnering with two farms in a Western Sierra professional producer grant, investigating the elasticity of biochar and diving deeper into its effects on the seed cycling, specifically trying to utilize Min-C and epoxy to get at what's going on in that seed cycling. Thank you for your time, and I appreciate your patience.